Hello everyone, welcome to Linear Algebra 2 fourth problem solving session. Today we will solve the remaining problems from the problem set practice problems for quiz 3 and quiz 4. I will start with question 11, which is show that if t times t adjoint is equal to 0, then t is equal to t adjoint and this is equal to 0. We need to show this one. Now, let's start the proof. Now, take any u, take any v from me. Okay. Now, we have t adjoint v is equal to. Now, we know that t adjoint is equal to 0, so this part is equal to 0. Since if one component is equal to 0, inner product or Hermitian inner product is equal to 0. Now, we have this one, and we can take this one here from the properties of adjoint. This is equal to t adjoint v. So we have this one. So, since t adjoint v is equal to 0, this implies that t adjoint v is equal to 0, right? This is the one of the properties of inner product. If vv is equal to 0, then v must be equal to 0. V must be equal to 0 vector. So dv is equal to 0, but we take the v arbitrary. So this equality satisfies for every u. This is true for every v in v. So we have t adjoint is equal to 0. Now we need to show that t is equal to 0. Let's look at the tv. Now, tv is equal to. Now, if I take t adjoint here, we have v t adjoint tv. Now, we know that this one is equal to 0, right? This operator is equal to 0. So this is t adjoint of t of v is equal to 0. So this one is equal to 0. Now we have again tv is equal to 0. So tv is equal to 0 for every v. Still, our v's are arbitrary, so this is true for every v. So t is equal to 0. So we find that t is equal to t adjoint and this is equal to 0 operator. Question 12 is, let v be a finite dimensional Hermitian inner product space and t a linear operator on v. Prove that t is normal if and only if norm of tv is equal to norm of adjoint tv for every v in v. First, let's prove the easy sides. If t is normal, this satisfies. Let's say t is normal. So, if t is normal, this implies that t adjoint t is equal to t times t adjoint. So, let's look at the tv. Now, we can take this adjoint from here. So, we have v t adjoint tv. So, then we have now we have that t adjoint t is equal to tt. Let's use this one, tt adjoint v. Now, again we can use the property of the adjoint. So we can take this t from here as a t adjoint. T adjoint v is equal to t adjoint v. So, ttv is equal to t adjoint v. And we know that tv is equal to square root tv, and we prove that this is equal to square root t adjoint v. So this is equal to norm of t adjoint v. So we prove the easy side. Now we need to prove the second side, which is if this is true, then we can say that t is normal. Now, from here, we have that, so this implies that square root of TV is equal to square root of t adjoint b, t adjoint v. So we will have that, if we take square of each side, we will have TV is equal to t adjoint b, t adjoint b. Let's take first t and first t adjoint to the second side, so second component. So we will have this one will be equal to b times t adjoint tv, and this will be equal to b and t adjoint b. This is t because adjoint of t adjoint is equal to t. So if this one is equal to 0, we will have v of t adjoint t minus t adjoint v of v is equal to 0. But we need to show that whether this one is equal to 0 or not. Maybe they are like orthogonal to each other. It doesn't mean that like one of them must be 0. So we need to show that this one is equal to 0. Now, some facts about this one. You know that this one is self-adjoint, right? TT and TT are self-adjoint. So T star T minus TT star is also self-adjoint operator. For simplicity, let's say that T star T minus TT star is equal to, let's say, operator S. Now, we need to prove that V of SV is equal to 0 and S is self-adjoint, implies that S is equal to 0. Now, to prove this claim, we will use some facts. Now, since S is self-adjoint operator, we have that S has an orthonormal basis of eigenvectors consisting of eigenvectors v1 up to vn. This is an self-adjoint operator. Now, let's take any w from this set, v1, vn. Let's say lambda is the corresponding eigenvalue. Then we have SW, right? And this is equal to 0. And we know that SW and this is equal to 0. And we know that SW is lambda times W. So this is equal to lambda W times W. So we will have lambda times W is equal to 0. Alpha WW is equal to 0, right? So this implies that lambda must be equal to 0 since v1 to the vn was the element of the basis, so it cannot be equal to 0. So lambda is equal to 0. So, and we choose this v as an arbitrary on the set. So for every eigenvector, eigenvalue is 0. So we have only one eigenvalue, which is 0. So characteristic polynomial will be equal to x to the n. So, since characteristic polynomial is x to the n, so we will have s to the n. So, we know that if normal, okay, here self-adjoint implies it's normal. So since it's normal, if it's nilpotent, then s must be equal to 0. So this completes the proof. S is equal to 0. So we prove that this s is equal to 0. So after the claim, s was t conjugate t minus t conjugate. So t conjugate t minus t conjugate is equal to 0. So t conjugate, t adjoint is equal to t adjoint t. This completes the proof of the question. Now, question 13 is let B is equal to n by n matrices over complex number equipped with the Hermitian inner product, or let's say it's not inner product right now, AB is equal to trace A times B adjoint. Part A, show that this product is an Hermitian inner product on B. Part B, suppose that P is unitary matrix. Show that the operator T on B defined by T of A is equal to P adjoint is a unitary linear transformation. Now, first we need to show that this one is a Hermitian inner product. Before that, I want to understand that what is this product. Now, let's say A is the matrix Aij, entries of the A are Aij's, and entries of B's are Bij's. And trace of A times B conjugate will be equal to I from 1 up to n, J from 1 up to n, Aij times Bij conjugate. Now, why this happen? Let's look at. Now, entries of A are A11, ANN, AN1, and A. This is the A, right? And the B conjugate was, B adjoint is B transpose conjugate or B conjugate transpose. Now, so the entries of this one, at the A11 we have B11 conjugate. Now, here we don't have, A11, A1n, we won't have the B1n, we will have Bn1 since we take the conjugate. Then here we will have B1n conjugate. We will not have Bn1 since again we take the conjugate, and Bnn conjugate. Let's look at the multiplication. So here, for example, this time this is equal to, at the first entry, at the 1 entry, we will have A11 plus B11 conjugate. Here we have A12, right? And we have B12 conjugate plus A12 B12 conjugate. And this go like this, and we will have A1n times B1n conjugate, right? And every middle entry we will have the same results. Let's say at the kth entry we will have AK1 times BK1 conjugate, AK2 times BK2 conjugate. Something like this. Let's look at for example, let's look at the last one. Let's look at the place NN. I'm just looking at the entries at the diagonal because for the trace we only need to do entries at the diagonal, right? Trace is equal to addition of entries at the diagonal, right? So for example, at the place ANN we will have AN1 times BN1 conjugate this goes like this, A and N times B and N conjugate, right? So this was the what is doing on the A times B adjoint. So trace of this one, addition of every this one, so we will have I from 1 up to N, J from 1 up to N, Aij times Bij conjugate. So now we need to show that this is an Hermitian inner product. So first thing we need to show that trace A plus BC is equal to trace AC plus trace BC. Again, let's say A is equal to Aij, B is equal to Bij, and C is equal to Cij. So this one, trace A plus B, C is equal to I from 1 up to N, J from 1 up to N, ijth entry of A plus B is equal to Aij plus Bij, right? This one times Cij conjugate. This was the sorry, this is not the trace A plus BC. This is the product A plus BC, which is trace A plus B times C adjoint. So this is equal to this one. So we can distribute the Cij conjugate inside. So we will have this is equal to I from 1 up to N, J from 1 up to N, Aij times Cij conjugate plus Bij times Cij conjugate. So since this sum and this sum does not depend on each other, so I can divide this sum into the two sums, which is I from 1 up to N, J from 1 up to N, Aij times Cij conjugate plus I from 1 up to N, J from 1 up to N, Bij, Cij conjugate, and this is equal to A product C and plus this is equal to B product C. Now we will have what we will have. First thing is okay. Now we need to show second property, which is trace of C times A B. Sorry. Okay. So this is not this one. At the first property, we show that product A plus BC is equal to product AC plus product BC, and for C times AB is equal to C times AB. Now we need to show that this one C is in the complex numbers. C is a scalar in the complex number. Now we need to show this one. So again, A is equal to Aij and B is equal to Bij. So C times AB is equal to trace of C times A times B conjugate. So this is equal to I from 1 up to N C times Aij times Bij conjugate, right? Now this sum doesn't this C doesn't depend on the I and G's, right? So we can take C outside, so this is equal to C times I from 1 up to N Aij Bij conjugate. So this is equal to C times A product B. The second property is also done. So we need to show the third one, which is AB, product AB is equal to BA. Now again, let's look at what is this one. A product B is equal to I from 1 up to n. Sorry, there is J from 1 up to n here. J from 1 up to n here. Okay. So I from 1 up to n, J from 1 up to n, A, IJ, Bij conjugate, right? So we can take 2 times conjugate of this number, then it will give us again the same thing, right? Let's say k conjugate will be equal to k for every complex number. So if I take the conjugate of conjugate, this thing, let's say conjugate, Aij, Bij conjugate, we can distribute this conjugate inside. We will have I from 1 up to n, J from 1 up to n, Aij conjugate Bij. So this is equal to I from, there's also conjugate here, I from 1 up to n, J from 1 up to n, Bij times Aij conjugate, right? This is just a regular product, so we can, the numbers are commutative, so we will have this one and this is equal to BA conjugate. So second property is also okay. I mean to show the third one. Third one was, sorry, we showed the third one. We need to show fourth one. Fourth one is to show that A greater than or equal to 0 for every A in n by n matrices over C, and AA is equal to 0 if and only if A is equal to 0. Now, let's show that AA is equal to 0. Now, we need AA is equal to I from 1 up to n, J from 1 up to n, Aij times Aij conjugate. So, okay. Now, Aij times Aij conjugate. Now, this was the square of norm of Aij, right? I from 1 up to n, J from 1 up to n. Every Aij is in the complex number. Norm of Aij square. So, norm of Aij square will be greater than or equal to 0. So, every segment of the sum is greater than or equal to 0. So, this one greater than or equal to 0. Now, since every segment greater than or equal to 0, if this one is equal to 0, every segment must be equal to 0. So, since norm of the entry is equal to 0, Aij's must be equal to 0. So, since every entry for every Ij, since every entry of the matrix is equal to 0, A is equal to 0. So, this completes the first part. So, it satisfies four of the Hermitian inner product properties. So, we can say that now this one, this product is a Hermitian inner product. Now let's again remind to the part B. Part B was suppose that P is unitary matrix. Show that operator T on V defined by TA P adjoint is unitary linear transformation. Now, unitary matrix means that, let's use this one. P is unitary implies that P times P adjoint is equal to identity. Also, P adjoint times is also identity. So this means this is unitary. Now, also TA is P conjugate, right? Now we need to show that this is unitary linear transformation. So we need to show that TA, we need to show TA TB is equal to AB for every AB, matrix AB. Now we have TA times TB is equal to TA was PA P adjoint, TB is TB P adjoint. So this is equal to trace of PA P adjoint, adjoint times PB P adjoint. So this adjoint is equal to PA P adjoint times P B adjoint P. Okay. P B adjoint P adjoint, right? Adjoint of this one. Now, since this is unitary, P is unitary, we know that this is equal to identity. Okay. So we can see that this is equal to trace P A B adjoint P star. If we see this one and this one as a two matrices, and trace operation is commutative. This means that recall that trace of A times B is equal to trace of B times A. Because of this one, we can say that this one is equal to trace of P adjoint times PA B adjoint. Again, since P is unitary, this is identity. So we have trace of A B adjoint. So this is equal to A product B. So this is what we need to show. This completes the proof. Question 14 is, suppose that T is self-adjoint operator on an n-dimensional inner product space with k distinct eigenvalues lambda 1 to lambda k. What is the minimal polynomial of T? Now, we know that T is self-adjoint operator, right? So T has n-dimensional orthonormal bases, and the elements of this basis are the eigenvectors of T. So there is n-dimensional eigenvector space. So we can say that now T is self-adjoint. Means that T has n distinct eigenvectors. Now, since T has n distinct eigenvectors, that all these ones are the eigenvalues corresponding to these eigenvectors. So we can say that we have these eigenvectors, and we can say that so characteristic polynomial of T is equal to x minus lambda 1 to the n1, and it goes up to x minus lambda k to the nk. So this is the characteristic polynomial. We need to find the minimal polynomial. So let's say fx is equal to x minus lambda 1 to x minus lambda k, right? So since this is fx, and also say m is equal to maximum of m1 to nk. And characteristic polynomial divide fx to do by m, right? So from Cayley Hamilton, says that ft to the m is equal to 0. Now, we have that self-adjoint implies that t is normal, right? And t is normal implies that ft is normal. So we have a lemma. This lemma says that if some operator is normal, then, and if this operator also is nilpotent, which is f to the m is equal to 0, from these two facts we can say that ft is equal to 0. So this was the minimum. So this implies that fx is the minimum polynomial of t. So this answers the question 40. 15 is, let A is equal to one of this matrix. Verify that A is normal and find the unitary matrix U such that U adjoint A times U is diagonal. Now, we need to show that this matrix is normal. To show that A is normal, we need to show that A conjugate A times A adjoint is equal to A adjoint times A, and A adjoint is A transpose conjugate, so which is 1 minus I. This one coming from here and this one coming from here, since it's symmetric. This will not change. 1 minus I, 1 minus I, 1 minus I. And exercise for you, A times A adjoint times A is equal to 4, 0, 0, 0, 4. So this matrix is a normal matrix. If you show that this is normal. Now we verify that A is normal. Now we need to find unitary matrix U such that U adjoint A times U is diagonal. To find this, we need to find eigenvalues and eigenvectors of A. Now, as we did a lot of time, we will look at the determinants of xi minus A, and this will give us, this is also exercise for you. We did this thing a lot of times. X minus 2i, x minus 2. So eigenvalues are 2i and 2. And if you try to find the eigenvectors, you will find the spaces lambda 2i will be equal to space generated by 1, 1. Exercise again these ones. Lambda 2 will be 1 minus 1. Now, these ones are two spaces. But since we want to find unitary matrix U such that it's diagonal, we need to, let's say this is V1 and V2. We need to make this V1 and V2 are normal. So, also we need to make these ones are orthonormal, but these are orthonormal. Let's look at standard product corresponding to standard product. V1 times V1, 1 times 1 plus 1 times minus 1 is equal to 0. So these are the orthogonal. We need to make these ones are orthonormal. Let's say V1 dash will be equal to V1 over norm of V1, and norm of V1 will be equal to, let's do that here, norm of V1 will be equal to square root 1 times 1 is 1, 1 times 1 is 1, square root of 2. Norm of V2 will be equal to 1 times 1 minus 1 times minus 1 is 1, 1 plus 1 is square root of 2. So this one will be equal to 1 over square root of 2, 1 over square root of 2, and V2 prime will be equal to 1 over square root of 2 minus 1 of square root of 2. So these are the corresponding V1s, and V2s are orthonormal ones. So U will be equal to 1 over square root of 2, 1 over square root of 2, 1 over square root of 2 minus 1 over square root of 2. 216 is find an orthonormal basis for R cubed such that the matrix of the operator Txyz is equal to this one is diagonal. First, let us find the matrix of the Dissipater corresponding to standard basis, which is 1, 1, 1. Standard basis 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Let's find this one. So this one will be equal to minus 2, 1, 1, 1, minus 2, 1, 1, 1, minus 2. Now, let's find the eigenspaces of this one. Exercise for you. Eigenvalues for this matrix are 0 and minus 3, and eigenvectors are beta 0 is only consisting of 1, 1, 1, and basis minus 3 is only consisting of minus 1, 1, 0 and minus 1, 0, 1. Please verify these things. I'm not doing this one because we did this thing adults. So now we have this one, but we need to find, since we need to find the basis which makes the matrix of T is diagonal, we need to find orthonormal basis. Now, we need to find orthonormal basis. Now, 1, 1, 1 will be orthogonal to minus 1, 1, 0 and minus 1, 0, 0, 1, since like these are corresponding to 0 and these are corresponding to 3. Let's look at that. Now, we need to use the Gram-Schmidt orthogonal process, and we need to find the orthogonal basis, orthogonal version of B minus 3. So let's look at, first let's try to see V3, V2 are not orthogonal. V3, V2 corresponding to standard product, we will have 1 plus 0 plus 0 times 1, 0, it's equal to 1. So this is not equal to 0, so V2 and V3 are not orthogonal. So we need to use the Gram-Schmidt process and find orthogonal base. Let's say W1 is equal to V2 and W2 is equal to V3 minus V3 V2 over V3 times V2. Sorry, V2 times V2. So V3 V2 we find that is 1. Now we need to find V2 V2 is equal to 1 times 1 minus 1 times 1, 1 plus 1, it's equal to 2. So we will have W2 will be equal to minus 1, 0, 1 minus 1 over 2 minus 1, 1, 0. So this is equal to minus 1 plus 1 over 2 minus 1 over 2, 0 minus 1 over 2, 1 minus 0 is 1. When we use these vectors, 1, 1, 1, minus 1, 0, minus 0, 1, sorry, this is not the minus 0, 1, we find this one as minus 1 over 2, minus 1 over 2, 1. So this is the orthogonal basis, but we need to find an orthonormal basis. So we need to divide these ones are the norms. This one is V1, W1, W2. Let's find the norm of this one. V1 will be equal to 1 plus 1 plus 1 will be equal to 3. So norm of V1 will be equal to square root of 3. V2 W1 will be equal to 1 plus 1, 2. So norm of W1 will be square root of 2. And W2 will be equal to 1 over 4 plus 1 over 4 plus 1 will be equal to 6 over 4. So norm of W2 will be equal to square root of 6 over 2. So new orthonormal basis will be 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. And second one will be minus 1 over square root of 2 minus 1 over square root of 2, 0. And third one will be 2's are cancelled, minus 1 over square root of 6 minus 1 over square root of 6 plus 2 over square root of 6. Let's say these are S1, S2, S3. This is the our matrix, the matrix we are searching for. Let's try to verify that. Okay, if you try the computation, TS1 will be equal to what was the 0, which is 0 times S1, and verify these ones. TS2 will be equal to minus 3 times S2, and TS3 will be equal to minus 3 times sorry, this is S2, this is S3. So question 18 is, let B be the vector space of complex valued continuous function of 0 to 1, equal with integral Hermitian product fg 0 to 1 f times conjugate g of x dx, let h be in V and t be a linear operator on V defined by the formula t of f equal to h times v. Show that t is unitary operator if and only if h of x is equal to 1 for all x. Let's do the first side. T is unitary means that tf times tg is equal to f product g. Let's choose g is equal to f. So tf will be equal to tf was the h times f, and this is equal to 0 to 1. There's f times f conjugates. Norm of fx square times norm of hx square dx. And this is equal to ff, which is 0 to 1 norm of fx square dx. This is equal to this one. So we know that 0 to 1 norm of fx squared times norm of hx squared dx is equal to 0 to 1 norm of fx squared dx. So from here we can say that we can take this one this side. We will have 0 to 1 fx squared times norm of hx squared minus 1 dx is equal to 0, right? Now, this is greater than 0, right? Since greater than equal to 0. This is 0. Let's say fx is not 0, so this is 0, since this is true for every f in V. So we will have hx minus 1 is equal to 0. So this implies that norm of hx square will be equal to 1. So norm of hx will be equal to 1. Now we need to show that this side, we will assume that norm of hx will be equal to 1. Now, so we need to look at any TF, TG. These are any f and g. So, TF, TG will be equal to 0 to 1 f times g conjugate x times hx norm of hx dx, and we know that this is equal to 1, so we have 0 to 1 fx times gx conjugate dx. So this is the product fg. So T is unitary. So this was the last question of this problem solving session. So see you next time.